Another draft science video presentation. Fish, yes. So, I would argue that we're like these fish. We navigate our world and try to find these little things that intrigue or please us. Our eyes are averted and we go there and see what's interesting, blah, blah, blah. And so I'm making these physics videos and some effort to be like some little squiggly thing that catches the eye and you say, yes, I'll go there, see what's happening. And it's because you have to be sort of hungry for something, looking for something more, something different. And I understand that. I wish there were some place I could go besides a fish tank, to find something worth watching. But even this is sort of annoying because, I found that these videos are marked as if they're live, live. And they're not live. They're just, recorded video of fish tanks. And it's like everywhere you go is just deception, Everybody is so dishonest and it gets rewarded. People fall for it. I mean, there's like 400 people watching this recorded video that says it's live, and they're, talking about what's happening not live. And it's kind of pathetic. So yes, you're doing something better than that. So you'll see, it says here live. So, I wasn't on the live part there. It's live now. It's not really live. You can just see they keep switching the fish tank. Keep switching the view. It's just fake. Now this one actually is live. So I'll give them credit because it's actually live. It's some crappy bay in Miami. So not much happening. It's not as cool as the fake worlds they create. And blah, 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 blah. So, not just I have to make a commentary here and there because it's sort of connected. That's what I would argue, is that you can see the connection between, these kinds of facts of reality and the fact that physics is existing in the same world where it's just a show now. It's just a story they tell, and they put a bunch of plastic into the story and a bunch of fake stuff and nonsense and gibberish. And it, some of it honestly and some of it quite obviously, I'm arguing quite dishonestly, because you don't need much brains to see through the bullshit. And it's hard to imagine that all of them are that stupid. But they start getting fooled by the fakery and the shenanigans, and they think that's what physics is it becomes more plastic than the reality. That's sort of what I'm saying. So in that vein, I'll talk again some more about the two-slit experiment, just play some more with what we have learned over the last few months. And it all kind of fell together in the last few months. It did, for 10 years, I kept looking at the plastic coral and the this and the that, and I kept thinking that was the reality, and I kept trying to figure out, well, why are the fish all shaped in certain ways, and they don't seem to be eating that stuff, and what do they eat? And, they're fed pellets, and, so, they're not really eating the environment. They're not really living in any kind of real world. They're living in a synthetic, fake, phony, bullshit world. And, physics has done the same thing. It's just created a bunch of assumptions and drew some conclusions. They're just loop-de-doo stupid, and, and they won't admit it. They won't, like I said, it doesn't take much brains. I don't have much brains, so to speak. I mean, I didn't train as a physicist. I didn't spend every day fiddling with this stuff and saying, what does it mean? What does it mean? I have to say, I did always say, what is it, I was always curious as to the function, but I hadn't gone deep enough to see that the function isn't what they've made it out to be at all. It's, and in some ways, like I said, it's just such an obvious that it's so what they're saying just isn't the truth. They're not describing the reality. They're describing a premise for, the glue that they're using to stick everything together, and it's just glued on. All right, so leave us go through some of the stuff that's really kind of obvious. All right, so you just have this basic thing of the single slit. We can do that first, I suppose, and it ends up being the same as the single impediment in terms of the rules. It's just about the distance between two surfaces. That's all it comes down to. And so it, they imply that it's not about surfaces. People like Richard Feynman are famous for converting it into some notion that if there's automatically some kind of randomness created, and it doesn't matter whether the photon goes in here, it goes in here, goes in here, it doesn't make any difference. It's all going to be randomized by the random gods, and sort of indicating that if you did the same thing, over and over again, that you would get different results. That if I set up the universe where I actually just sent the photon right by the surface, and I had another universe where it goes right through the middle, that I shouldn't have any expectation that this universe would do something kind of the same each time, and this one wouldn't. This would be that there would be very different universes, and he would argue, no, they'll have the same kind of randomness built into them. And you can just logically say, no, come on, you can do better than that. You should be able to do better than that. So anyway, what's created is a pattern, okay, and the pattern has key features that are kind of, you can dissect it and know that it'll do certain things. So if I make the slits narrower, if I put more, and so we have less coming in, then we know the pattern is going to get just spread out. It'll have the same features, it'll just spread out. Okay, so it'll go wider. So I'm not drawing it wider, but it's wider in all respects, just stretches out. And the wider it is, the smaller this distinction gets. And so that's a feature. And that's shown in the math, essentially, because the math is basically saying this distance is kind of important here, and then this distance is kind of important here in terms of telling you how big the pattern will be. Obviously the further away you go, the more you're amplifying, you're magnifying the image. So the closer it is, the smaller the image, the further away, the bigger the image, so it's like a microscope. This distance, I'm going to call that L, because that's usually what they call it, or something like that. So the math is just saying, okay, let's take the distance, and then the wavelength of the light is the other key ingredient. So between whatever 300 and 700, you put in your light, and it'll decide what these points will be. And so the first thing that you should be able to figure out is that this L distance, if I'm going over here, I can't, unless I change the length, the L number, this line is going to be a lot longer than this line, and this line is going to be a lot longer than this line. So if I'm using the same L in the math, then the first thing you can figure out is, the math isn't going to predict this location. It's going to predict a location, on this arc. So that's the first thing, the first deception they give you, is that you're actually predicting a pattern on a flat screen, when the math clearly only has one L in it. So you have to stay that L distance. You can't make the distance longer, okay, and pretend that you're getting the right answer, because your triangle that you end up creating, between your two surfaces, you're creating a triangle. That triangle is going to be very different. The length of this hypotenuse is going to be a lot different depending on the fact that I broke that L. So right there is the first, oh, okay, these guys are all mathematicians. They should have noticed that right away, right? I mean, can we really believe that these people doing all this complex, intricate math haven't figured out that that L can't get longer. You can't put the same number in, all right? The L has a number, like 3 meters or something. It has a real number. And so that L is refined. So your answer is going to be for here. Your answer isn't going to be for here. Your answer is going to be for here. You know, this distance is the one it's going to be telling you. It's not going to be telling you this distance. So anyway, you know, this, you know, like I said, you learn this, you say, oh, this is so obvious. Why isn't that part of this story? All right. And then the other part that's kind of, you know, becomes kind of obvious is all they're doing, they divide the distance, okay, into the wavelength and then do their sine theta math. You know, they're doing angled math, you know, but you don't have to do any of that. Okay, you can make it the same variables. I'm just saying, let's just use the same variables and not get into the complexity of a sine theta. And all you're really doing is you're just saying how many wavelengths fit inside of this distance. So you're just really saying, just take the wavelength and put it into the distance, and that'll tell you exactly how many wavelengths fit in the distance. You know, so if it's so you could use real numbers, and I'm afraid to do that at the moment just because 500 nanometers is, let's say that's the light. So you can see that's a half of a 1 here, so that would be like half of a micron. And so you can just say, however big I make this slit, just how many of these 500s fit into how many of those. And you could say that something like, I would guess, see, I should have done this ahead of time, that like a ½ millimeter. Okay, so if you had 0.5 of a millimeter here, and you put 500 nanometers into it, you would get something like 1,000. Let's just say. So the 1,000 would be telling you that there's actually 1,000 locations on this arc. Okay, the total on this whole arc, there'd be 1,000 of these little nodes. So it's basically just telling you how many times the whole wavelength, the whole this distance goes into this. But the truth is when you actually do this math, you know, it's going to be 535. And this number might not be 0.5, it might be 0.521. So when you do this, you're actually going to end up with numbers that aren't going to be perfect whole numbers. And the even numbers, you know, are going to be different than the odd numbers in terms of splitting them in half, because the half is going to be right here in the center. So that's part of what can give this away. So once you know it's on an arc, and once you know that all you're really saying is how many wavelengths are in here, and if it turns out to be whatever number, let's just say 250, that's just telling you how many places it's possible for you to have two lines from these 2 points and have those 2 lines be exactly a full wavelength divided into. It comes out a whole number. All right, no remainders. So the 2 have exactly the same number, a whole number. This one might have 10 and this one might have 15, but they're whole multiples of the wavelength. And there's only this many spots where that can possibly happen. So you can see the geometry gets really obvious and kind of simple, and that, you know, when you really figure it out, it's all about what's happening on these surfaces, and it has nothing to do with what goes through here in the center. And that's sort of the giveaway. In the single slit, another distinctive feature is this gets very, very bright. So like 80%, 90% of the light will go right here. All right, 90%, you know, of it hits right there in that center, and the fringes are just a tiny percentage of the light. And that makes perfect sense in the sense that you're figuring that yes, a lot of the light just can make it through the middle, but it's only the light that's interfering with the surfaces. That's the only place it's getting affected, and their math proves it because they're basically just telling you overtly, this is where we're going to draw our vectors from, these point sources. The point sources are everything, the surfaces. That's the difference between the 2 point sources, and you're just saying, you know, kind of obviously. And so this makes more sense intuitively because you can sort of understand the closer I make the slits, the higher the percentage likelihood that a photon is going to interact with the slit, right? I mean, the closer I bring them together, the more the more unlikely it gets that something can go through without hitting one of the surfaces. And the pattern shows that, because as I narrow the slit, the other feature that takes place is this brightness goes away, and this becomes all the same intensity. All of this light becomes very similar. Okay, so you lose all of the brightness here. It's not bright anymore. So the narrower I make the slit, the less bright the center gets. So that's completely consistent with just understanding that everything is happening here on the surfaces. That this isn't about some photon breaking into two photons and then doing all this nonsense. It's just about the fact that surfaces are causing the effect. And that fits because light's small, okay, even though it's really big. I mean, this wavelength, 500, let's say, is, 10 times, 100 times, 1,000 times smaller than the size of an atom. I mean, an atom is 0.5 nanometers. So this is a lot bigger. 500 nanometers. I don't know why that points there. Is a lot bigger than the size of an atom. So photons have a polarization that's pretty big, or a frequency. Their wavelength is large compared to the size of this opening. And there's a proportional relationship between wavelength and polarization. We find that from radio antennas and stuff like that. And light's doing a similar thing. So one can have the expectation, that's why a wavelength is significant. And when I get really, really small, or I put the slits very close together, what I'm also doing is meaning the 2 point sources end up being, when they're far apart, they're easy to see that it's two spots. But if I put them closer together, it gets harder and harder to see that it's two locations. And that, this 2 becomes just a 1, And so then you get no pattern. And the same is consistent with what the outcome is. So, so all you're really doing is saying how many wavelengths are in here. And you're just projecting it onto this line. So you're just making a longer line, okay? So you just take this distance, the distance of this radius, right, the L number, and multiply it by pi, and that'll tell you this length. And so all you're doing is saying, divide the same number of wavelengths here into that bigger line, okay, and that'll just tell you where all these little nodes are. And what it also can tell you, right, what you can also figure out or discover, I will erase this, is that you can, quite accurately, you can do this to some accuracy in terms of you can recognize that the most difference between, the biggest difference in wavelength will be this difference, right? That's the math. That's, you're basically just saying what's the difference between this line and this line is the number of wavelengths between the two slits. So that's the biggest difference you can have in the vectors. The length of the lines would be at 90 degrees. And so all you're really doing is saying what's the, divide the wavelength into the distance, and that'll tell you exactly how many wavelengths fit in. And if if it comes out to be, let's just say, let's use a small number because it's easier to use, 14.5, well, that's telling you it's not a whole number. So this has to be a half of a node. So it's somewhere on a destructive interference, in the sense that you're not going to have a whole number, so your pattern won't be put back together. So the argument is that the photon is something like this with an equidistance between the bits, and you have a number that's not equidistant. So you can tell that this is going to be an off. And so you can say that your first node would have to be that distance you found, how many nodes there are going to be, and you'll know that this one's an off. Now what you'll also know is when you cut this in half, right, you know that this here, the center, is going to be half of this number. So it's going to end up being 7.25. Now that's not going to be the same distance either. That's not a whole number of wavelengths, and it's also an odd number of wavelengths. So it means you have 7.5 on one side and 7.25 on the other side. And so right here can't be a matching, even though this has to be the same distance as this here, okay, based on the real pattern that you're really creating, it's an off. So the facts say it's an off, the math says it's an off here, but these little vectors say it's an on. Well, that's just an illusion of the fact that you can't draw this experiment to scale. I mean, I can't draw 3 meters worth of distance. So what's not realized, what they don't tell you, is that these two equidistant lines are happening inside of this tiny space, 1 millimeter. And that's true all the way, okay? It stays inside that 1 millimeter. This pattern of these two equal lines, that pattern never escapes being inside that 1 millimeter. So even at 3 meters, and say this was a centimeter, these notches, the pattern of these two lines is happening inside this little thing here. Okay, that's where this pattern is being created. That's where the on is, inside that tiny, tiny little space. And the real pattern, is out here, and the real pattern is doing this, right? This is where the node is, and the other node is over here, right? And so you can kind of figure out that that's why this is bigger. So physics never explains why this is larger. The simple explanation is because this is a lie. I mean, this is happening inside of 1 millimeter. The real pattern is happening over this whole scale, and it started with what your number is between your distances here. And if your distance isn't a whole number, and it's not an even number, okay, like say if I just said it was 15, well, you know that if it was 15 here and it was an on, right, because it's a whole number, there's no remainder, 15.0. Well, then this would be 7.5. So there is a remainder. So you know it can't be an on at the center. It has to be some off point. And so now the on will be here, and the other on will be here. And what all you're doing is filling in the space between them. So it's really two nodes, okay, very close together. Well, close enough. And the fact is all the light that goes through the middle is just filling this in. So the light that gets through the middle just fills that in, and you don't see the fact that that's really an off. Plus, you have this little tiny bit of light that also comes, that's also going in here, okay, deflecting this way. That's creating a bright spot right there in the middle. So it just fills in, and so this ends up being a little more than 2. And it can be a little less than 2, but it's always bigger than 1. And yeah, so they don't tell you any of those facts. They don't point any of that out. But that's the simple truth. So when they go, well, we know this has to be the same distance. Well, it's only the same distance inside of this 1 millimeter. There's two patterns created, essentially. You can sort of understand that if each slit, draw it down here, if each surface is just scattering, that is, if it's just sending bits this way, then obviously you can see that each surface is sending not only stuff both going this way, but it's sending stuff, both going that way. So it's making two patterns. It's making a pattern that's going wider, and it's making a pattern that's going narrower. So it's making a narrower pattern in here, and it's making a wider pattern in the rest of the world. And the same thing happens with apertures and the whole interferometers, in a sense, because they're making two patterns. They're making one that goes in, one that spirals in and makes circles, and then there's one spiraling out that makes rings. And the two patterns are different. All right. So this one's essentially making little tiny bars, inside of 1 millimeter, and the other one's making big bars, much bigger, because it's one of them is making the pattern smaller with distance, the other one's making the pattern larger with different distance. So that's the balance between them. But obviously only so much light can deflect that one way towards the inside. So I don't even know how to say that exactly, but the rest, obviously the ones that go more than that little tiny distance are the ones that end up going this way, and those end up being the ones you're really measuring, are the ones going in the same direction. So the key thing here is these two lines are going into each other, where all of the lines in the math, all the ones you're really looking at, are lines going in the same direction. You know, both lines going this way, both lines going this way. And only in this special case do the two lines go the same direction. And it's only a tiny percentage of the light that'll land there. Alright, so I don't think there's any other features of the single slit that need discussion. So it's a finite pattern. It doesn't have any infinities. The truth is that I would argue there's a mechanism here, obviously, that's causing the surfaces to be significant. So I guess we might as well say what that is. I'm arguing simply that photons are mechanical things. They're not mysterious things at all. And then all you're really doing is taking discrete pieces, quanta, clumps of energy, momentum, moving the speed of light. And you're just saying these clumps are at a frequency, and that becomes a photon. So let's say if you have 3 clumps, you have a photon. And the trick is every time an electron moves, it's clumping. Okay, it's taking stuff that was spread over space, right? So I have 3 things coming this way, and I move an electron this way. What I'm going to end up doing is taking those 3 things and making them take up much less space. Alright, so that becomes a clump. And if another electron does it over here, and I have another clump over here, you can see that what I've basically done is created 3 photons that have a distance between them of, say, 500 nanometers. So that explains both polarization, the fact that they don't fly at exactly the same, on the same vector, and it explains why you can't just create one photon, because one photon, one electron moving, creates the pieces that can be a photon, but it needs another electron to do the same thing to actually create the frequency between them, to synchronize them. And so all the experiment's really doing is, when surfaces can be understood to be covered in electrons, and that all you're doing is basically you're sending photons into a field of electrons, and the field of electrons will scatter the photons. It'll send them in all kinds of directions. And what it's really saying is that the little quanta, the little bits that you have paired at a distance, will be sent to different places. Okay, when it goes through the surfaces, the bits of the photon are scattered to all these locations, and all you're doing is saying, where do I put them back in phase? Where are their frequency correct? If I do it when this number is uneven, the wavelength difference is uneven, well, then I didn't create the frequency again. I have the wrong frequency. They're not aligned up at the right time interval, and so I won't get a photon. I won't hit the surface in the manner it needs to be hit to register an electrical impulse, and that's how we detect photons. The energy has to hit a surface, an atomic surface, and it has to hit it in such a way, at such a timing, that it causes movement through the crystal or whatever of the material, and that movement eventually moves an electron that causes a cascade of pressure that we call a voltage. But that's a photon. A photon has to cause a voltage for us to call it a photon. Anyway, so the energy is going to all the locations. So the places that are dark are really being hit by little bits of energy. It's just heat as far as they're concerned. It's just gravity. It's just the same. It's not recognized as a photon. So it's dark, but it isn't not getting hit by little bits of energy. The same amount of energy hits here as hits here. It's just not in a form. It doesn't have the right frequency to be a photon. So just like if I did a 2-source experiment with microwaves or something, the energy goes to all the locations. It's just some places the signal is jammed, like a radio. If I put an antenna and have two sources on either side of the antenna equidistant, and I put their signal out of phase with each other, then I won't be able to receive the signal here. I'll have to move here or move over here, but I won't be able to receive it here. Doesn't mean the energy didn't get there. Just means it's not in a form I can receive. And the same is true for light photons. The same rule applies essentially. They have to have a specific frequency, a specific timing, to be able to cause a cascade in the material that causes electricity. All right. Is there anything else on photons? So this idea you could just think of as being a string. If I had a piece of string and I tie it to one of the distances and I loop it around and tie it to the other distance, and the L is the distance I go, you can understand I can move the loop of string, and if I put notches on this one indicating the same notches of the difference here, you know, the wavelength difference, as I move here, the notches will tell me right where the reconstruction of a photon will be, where I'm in phase, where I've taken the pieces from here, and I took a piece from here, and I sent them to the same place, and now they're back in phase. They have the right distance between them when they hit, and therefore be recognized as a photon. And so it'll tell me every one of those spots. And like I said, right here at the center, I'll understand that I'm going to have, you know, the same number of notches on both sides. And so if I have an even number here, I'll have an even number here. But if I have an odd number here, I'll have an odd number here. Something like that. A full wavelength. So, yeah. All right. So I don't think there's anything else on the subject of the single slit. All right. So maybe I'll take a break, since I can do that, hopefully. And I'll be back to do the double slit. Alright, I should be back in business. So double slit this time. Try not to be too redundant. And so this one gets more fame, okay, because it creates a more interesting pattern, but more because 200 years ago, this was the experiment somebody showed people to say, look at this weird, bizarre pattern. Now, Newton had already done these experiments. I mean, Newton has done, he put a single hair in front of light and found the pattern. He made a single opening and found the pattern. So he had done surfaces facing out, surfaces facing in, right? So you have, this is basically the slit opening, this is basically the impediment, right? So this has both components of what Newton had already discovered. And yet Young came along in 1801 and did a crude version of this experiment. Okay, didn't use monochromatic light, got a very, you know, blended pattern of, you know, colors, and he theorized, because he was a sound engineer, that this was just basically the same thing two audio sources will do. You know, that I can do this with audio, and I can have these two waves that will interfere in the space. Okay, the medium will compensate, the waves will do this destructive, constructive interference stuff and make a pattern. The problem is mathematically this doesn't have any hope of getting the right answer, because the point sources end up being here and here. So this simple analogy that all of physics uses all the time, I mean every single, just about, I don't think there's an exception, every single video on YouTube describing the two slit that does any analysis mathematically or shows you a description of what's happening, cheats and uses this diagram, this Jungian notion, when they know their math doesn't do that. So nobody does the math from this and here being the point sources. And I'll say, okay, nobody does it. Yeah, they do it in the exceptional cases. So the exceptional cases, like I said before in the other video, is when they make the impediment so small, less than a wavelength. Okay, so it's really, really tiny. Just a thin little hair, wire. Very, very, very small. Or they make the slits really, really small. Okay, and in those two cases, what's happening clearly is that you can't draw vectors, two different vectors from those locations, that have any significance, because they can't be a wavelength of difference. They can't be, I can't make a line that's a whole wavelength of difference between these 2 points, because it's less than a wavelength of difference here. I can't have a wavelength of difference in these lines if I don't have a wavelength here, right? So this part of the triangle has to provide you more than a wavelength, or this can't possibly be longer. So I obviously can't create any interference or any notion of a mathematically significant difference. And so what happens is, if you make the wire small enough, you've converted the double slit into the single slit. And if you make the opening small enough, you're converting it back into another single impediment experiment, essentially. You're creating 2 slits that are really small, and the only surfaces that matter are these 2, because these are the only 2 that have distance between them. And you're making the distance between these 2 surfaces irrelevant, because they're so small. So in those cases, you can end up with an average that might be this distance. If I make really tiny slits, obviously the average inside that little tiny slit is still going to be pretty close to this distance. You won't have enough difference between this average, or the distance between the 2 centers of the openings won't be much different. It'll be less than a wavelength of difference between these 2 surfaces, and therefore the math is basically just saying there's only one distance. You don't have more than one distance in the experiment. All right, so that's another. I mean, these people, again, they love their math. They love being precise. They love talking about how much precision they can multiply and divide things and get these. Now they can tell us exactly how many hairs are on an electron skin. LIGO tells us they can measure 1/10,000th of the width of a proton. They tell you they make these extraordinary claims about how precise they are, and yet they are overtly their foundational cornerstone experiment. The experiment. Richard Feynman says this is the experiment for quantum mechanics. This is the whole thing is made out of this experiment. This is the key to the whole thing. And in their key experiment, they're cheating so overtly, right? Every single video cheating overtly by drawing these 2 waves and pretending this experiment will produce the right results with those 2 waves. So if you do the experiment with any kind of reasonable openings, like 1/2 of a millimeter for these openings, and something like 1/2 for this math, okay, this is the wave centers, this is the point sources. No one will ever use it because it doesn't get the right answer. Okay, it won't get the right answer. It won't even be close. So all of those videos are not real. Okay, they're fake coral. They're, it's a glued environment. It's a fake theory. It can't happen that way. All right. Now they do have math that does work. So there are people who have paid attention and have realized they better fix this because it doesn't make any sense mathematically. So the ones who really care recognize that, oh, there is a mathematical formula that does work. Okay, that we have a distance to a target. Now they're still doing it with this fake notion of a flat screen, even though we only have one distance here. So that lie still exists. They still don't tell you they're really predicting the pattern on an arc. But what they do acknowledge is that the pattern going to be created is more complicated than just this distance. You can't just put this distance in and say, there, that's all I need. No, you have to recognize there's 2 distances in the experiment, so you have to have at least these 2 in. Now the fact is you're sending a vector from here, you're sending a vector from here, you're sending a vector from here, and you're sending a vector from here. So there's really, 4 distances, 4 vectors that you have to pay attention to. But you can generalize it to the fact that you really have 4 surfaces. So as I explained in the earlier portion, the single slit is really the 2 surface experiment, and the single impediment is the 2 surface experiment, and the double slit is the 4 surface experiment. That's what makes it. That's what creates it. That's what it's made out of. That's the whole story of it. All right, so I should get to the pattern, obviously. So the distinctive part is, so the single slit did this, and what the double slit is going to do is this. Okay, you might have 5 there, and you might have 3 here, and you might have 2 here, and that kind of thing. And so you can say it's a pattern, it's 2 patterns, but The only thing distinctive, the only thing that makes it a pattern is this glaring absence here, and the glaring absence here, and the glaring absence here. So it's the missing pieces that really define the existence of the pattern. So the pattern's just a byproduct of the fact that there's something, this is missing, this one is missing, this one is missing. That's the pattern, the secondary pattern. We call that the envelope pattern. So when they do an honest description of the double slit, first they do the real pattern, which is this pattern that's broken. So it's two patterns, right? You can see there's little dots, and then there's a bigger pattern, okay, here. And they have acknowledged that the bigger pattern is essentially the single slit pattern, in the sense it has the wide central maxima. You know, it has this double wide here. These nodes are smaller, okay, than these in the center one, and then it has this little pattern inside. Now if you actually do the math, like I said, with your four source math, they can make it very complicated because they're still doing all this sine theta stuff, so they don't do it the simple way where you just recognize you have two distances. You have the closest distance between two surfaces, and then you have df, so I can say d close and d far, and you just do the same thing. You just say how many wavelengths fit in those two different distances. And so obviously very few will fit in here, maybe 50, and maybe this will be 150. Okay, so you can sort of get what's taking place here. Is the 50 is essentially making this pattern. It's just sending bits that'll be in phase, okay, to these locations. So it'll be in phase from here to here. It'll be in phase from here to here. Okay, it'll be in phase from, you know, here to here. All right, and it'll be out of phase on the empty spots. So it's really just creating bits that are flying to those locations. And then what's happening from here to here is you got 150 of them. So those are the little ones. And the little ones, okay, are doing the same thing. They're, you know, in phase here. They're out of phase, then they're in phase here, then out of phase, and it's in phase here. Now it's in phase here, but the trick is it's only getting bits from these two surfaces, and it's not enough photons, it's not enough pieces. So it can't remake a photon here. There's not enough pieces getting there. And what you're really doing is adding this component. This is half of the pattern's strength is here, and half the pattern strength is coming from these two surfaces. It's 50-50. 50% of your pieces are coming from these two surfaces. 50% are coming from these two surfaces. So when you only have 50%, it's not enough. So you won't see anything. So you need the contribution from the top one plus the contribution of this one. And where those two don't match is where you have the empty spots. And where they both match, when they're both in phase, when this vector, you know, the vectors from here and here match, are in phase with the vectors from here and here, that's when you get a spot. So both contributors have to provide their contribution or you don't see the light. And if it's just one or the other, then you're out of luck. Then you get a nothing. And that happens in these locations. And so that math works. 4-point sources works. Okay, so I can't emphasize it enough that that's what works. So we know it's about surfaces. So this whole conversation about, you know, a photon comes in, you know, whether you think it's a wave or whatever you think it is, and it pops out two things, that isn't going to work. It has to pop out four things. And, you know, realistically, the only way you can make this out of wave mechanics is to say that a wave is created here, and then a wave is created here, and a wave is created here, and a wave is created here. You know, like somehow, you know, the energy go right through the impediment to create this wave or something. You know, what would be the magic of this little wave? Okay, because that's what you have to do to make it work. Is to have the waves centered right on the surface. And obviously this more simple explanation is, obviously you can sort of see, look, if I scatter light from a surface, you can see that makes something you could call a wave, right? I mean, it can look like it, but it's not a wave, all right? and nothing interferes in space. So again, the energy goes to this location. It's just out of phase. Out of phase. pH, phase. And that's it. That's all. There's energy going there. There's bits. There's pieces of a photon hitting here. But the pieces are not being put together. They're not going back into their right frequency. So even if you thought about it as waves, you can understand that if the wave's got a period, and then I recreate the wave in this manner, that this is going to be distinctively different than this. And all the real truth is that we know electrons are very sensitive. Hit them with a certain color light, and look what happens. I mean, I throw white light at me, and look what it comes back to you as. You know, all kinds of crap. So clearly, it's very specific things happen. It absorbs some colors, it reflects other colors. So if the frequency is a little different, if I just make the wave, you know, a little narrower, that one goes inside of the surface, goes into the surface and vibrates it and does all kinds of stuff and just comes back out as heat. Where if I hit it with this wider frequency, that one bounces off and flies back at you. Can't say it strictly bounces off, but it is not absorbed permanently. It's re-ejected. So there's clearly, electrons are very sensitive. They know what you're throwing at them. They can tell the difference. And that's all that's really happening in this experiment. So it's the same rules. I mean, it's the same arc, same distance rules. You're just saying what's the difference in the distance, how many wavelengths fit in here. Those would be two lines. Those two lines, I just arc those two lines, and I'll end up knowing that there are certain points where the notches will match. Those will be where the nodes of on are, on. And at the center, I'm going to have the same scenario where all four vectors can point and be equidistant, but it won't mean anything because it's just inside of this 1 millimeter. You know, that's not the truth. These two lines aren't the truth. The truth is, the real pattern is there's a node here and there's a node here. And again, you're doing the same thing where you're sending this at a millimeter's distance, and so you just fill in the distance between them, and that creates this illusion of this one being bigger than these. You know, simple explanation. Stupid chalk dispenser is not working. Okay, chalk holder, chalk thing, pencil. All right, so does it need any more? Is there any other key feature missing here? Have we already? Yeah, so the only thing to explain is that photons are just a pattern, and it's a pattern flying through space of what you could say would be a collection. So inside of this little thing, so this would be the photon. Its wavelength, that is its difference, the difference between where they are in space going this way, right? They're all flying parallel. And the difference between their distance here from this one to this one, this distance and this distance are proportional. The polarization to the wavelength. And then when you look inside of each one of these little bits, right, each one of the little bits was created by an electron moving. So an electron moved, an electron moved, an electron moved, an electron moved. And inside of each one of these little bits, if you look inside of it, all right, that's where the real quanta are, the real little bits. And so this pattern is really 3 photons. Could be 10, you know, just depends on how dense you want to make the quanta in the field. But, you know, there'd be these little bits clumped together, these little bits clumped together, and all you're really saying is that this is a photon, this is a photon, this is a photon. This is a photon, 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 this is a photon. That's why when you send them in there, the odds are, you know, that you're going to end up with, you know, all these pieces flying around at different places. And the fact is, though, they had a connection when they went in. Okay, they were associated in a pattern when they went in. The pattern got broken, spread all over. But the fact is that 50% of the time, okay, those pieces are going to end up back in this order again, and 50% they're going to be out of order. It's just the law of averages. So half the light is destroyed, and, you know, destroyed in the sense you won't see it. And it's not even half, right? Because we know the bright nodes are a little larger than the dark nodes. So when you actually make the real pattern, you will notice that it doesn't have to, the frequencies don't have to be absolutely perfect. Because what you'll see is that the bright spots are a little bigger than the dark spots. You know, the dark spots should be just as big as the bright ones, so to speak. But when you actually do the experiment, you'll see that the little on nodes are bigger than the off node, because they're allowing for a bigger difference. And if you know, so you have to understand that mathematically, you're really saying this is the destructive part. You know, the destructive part is the same size as the on parts. It's just that the on blends into the off a little bit, so it's not perfectly proportional. But it's really telling you where the centers are anyway. All you want to know is where's the center of the off, where's the center of the on, where's the center of the off, and those are always the same distance. Yeah. So anyway, so they just tell you all this, you know, fake stuff about how it can't be a particle. Particles can't explain it. Blah blah blah. Of course they can, and they explain it better and more completely in terms of telling you why there's that bigger maxima, and explain exactly, you know, how it's not a. So part of the argument would be is the experiment they never do, right? An interesting experiment that they never have done, as far as I can tell in the whole historical record. So would be to take the double slit experiment and actually put photographic film over here. You know, put a piece of film over here. You know, and and see if you can catch a photon that's made over here on the arc. You know, because it's really just a guess that it goes in all these places, right? So if it was a true random theory, you would be able to find photons here. You should have some expectation that if I wait long enough, I'll get one over there. Okay, but the truth is that if this happens because it's hitting electrons, there might be a limited number of electrons you can possibly hit. You know, so a photon coming in can only hit. See, if you hit one electron, you get moved a little bit. You hit a second electron, you get moved even more. And you hit a third one, you get moved even more. Yeah, you could go that way too, and you go this way. But the point would be is to hit 3 or 4 electrons to end up going at a steeper angle when you leave. These steep angles would become more and more improbable. And, you know, super steep, you know, at say, you know, 89 degrees, both of them sending a photon to 89 degrees might be theoretically impossible. It might be so improbable because you can't hit enough electrons to get deflected perpendicularly. You know, to have a deflection that's tangential or perpendicular to which way the photon went in might be impossibly improbable, but you just don't have enough electrons. The thickness of the material would have to be really thick. The slit thickness would have to be really thick, and the point would be is that if you start bending it, you know, a lot, then it's going to bounce off the surface and maybe go over here and then fly out. So it's not going to give you much chance of having a photon leave at this surface at that angle. Well, anyway, so they've never done the experiment. They've never put the photographic paper here, or put it here, put it somewhere other than right here in the middle. If they put it in these other places, then they can see how much light actually ever gets there, and they could know that the theory is wrong, because photons never really do go over here. They never really do make it over here. Just doesn't happen. Okay, that the pattern will just be in this much space and no further, because it just can't hit enough electrons to get scattered enough. The alternative theory is that every electron can scatter at any amount. You know, a single electron could scatter at just 1 degree or 10 degrees or 20 degrees. But the whole point of scatter would be another electron theory. The point of it is that when you hit the electron, it's bound to a proton, so it doesn't go the same direction as you hit it. It's not free. It's bound. So that means the electron turns. Okay? And so it turns, and by turning, when it releases the energy of the photon, it's going to release it in the direction it turned. You know, so that's the idea of how the light gets bent. And obviously that would happen differently on the surface. So as you get closer and closer to the end, you know, to the end of the impediment, you can understand that the free electrons are kind of spaced out. And so now you have ones that can go this way, and you have ones that can go that way, and they can go in all kinds of directions because they're much freer
to detach from the surface. So as they're going near the surface, they go pretty straight, 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 straight. And then when they get up here, they start going any direction. So anyway, lots of theories you can posit for this, the reason why electrons move funny. And they move funny because they're usually bound to a surface. So you can't hit one and have it go perfectly straight, because it's always being influenced by fields that are going to force it to do something a little bit different. All right, is there anything else left out here? I think that covers most all of the stuff that needs to be covered. I'm just saying it's clearly about surfaces. The whole experiment is just about surfaces. It makes a huge difference whether a photon, see, they'll never say these words. Huge difference whether the photon goes through here or whether the photon goes through here. The whole pattern is made by the photons that go next to the surface. All of the pattern. All of the stuff out here and out here, all of it is made by stuff that had to go by the surface. It's not made by stuff going through the middle. And that's an easy deduction, and one they never talk about, because it doesn't fit their silly photons or wave nonsense. It doesn't work mathematically. Understand, waves don't work. Particle scatter does work, and it's perfectly consistent with what your expectations would be. You should have no expectation that a surface is some flat thing and it doesn't have any electrons sticking out of it. Surfaces have to be understood. So this is another, I guess, one little extra point. You have to understand it. If you believe in atoms, if you believe that atoms are a nucleus that's positive and electrons out here, then you have to believe a surface is electrons. You have to believe it. You have to know that has to be the right answer. And that when a photon is traveling near a surface, it's going to have to hit electrons. It's just not going to be able to miss them. They're going to be sitting outside of the surface, collecting there. And that's how charge works. Charge is essentially electron gravity. As I pile on electrons, electrons are attracted to this thing. There's extra positive left over. These 4 electrons don't use up all of the positive this proton is creating, right? This nucleus is creating a come-to-me force, in the sense it's creating an absence of reflection, all right? And so an electron way out here is still going to see this proton. As long as there's not a whole bunch of, as long as there's not an electron directly in its path, it's going to see the proton. It's going to see the force of attraction, the existence of an attractive differential in the force around it. It's going to see that less stuff is hitting it from this direction than this direction, and it's going to move towards it until it reflects, until it gets opposed by the other electrons. So until it sees the other electrons, it's going to just see the positive and move towards it. So you can see you could pile on quite a few electrons on top of a surface, right? Here's the surface, and you've got a whole bunch of electrons, a sea of electrons on the surface. Really loosely held, not strong. You can knock them out really easy, but they're there. And when they pile up, that's charge. When they pile up, they're putting extra pressure on each other, because all the electrons hate each other. And so the full pressure of the proton gets realized, because all these extra electrons start pushing on the other electrons, and they start putting them under higher pressure. So you end up increasing the pressure in here on the atoms. The atoms get more pressurized because you've piled a whole bunch of electrons on top of them. It works as a theory. Yes, that's just, an explanation that theoretically fits the evidence. And I'm just saying it's really simple. No Heisenberg, no entanglement, no superposition, no photons figuring out where they're going to go and going there. None of that. Just a simple force and motion. Nothing. You don't need any extra bits at all. Just understand that momentum moves electrons, and then the momentum itself can be changed in its direction by interacting with an electron. Electrons scatter electromagnetic radiation. That theory is all you need. Believing that is all you need to understand why surfaces matter to photons. Okay. So I mean, let's understand. I would love for one of these people like AB Science did all of this years of physics, math junkie, likes all of this precision, talks about how quantum mechanics is the most predictive theory in the history of mankind, does all this great stuff. Show how I'm wrong in this analysis of your cornerstone experiment. Show how I have misinterpreted or bent or in some way made a crooked argument in any way whatsoever. How have I done a disservice to the truth in anything I've said in this video? Will any of these people have the guts to explain how I'm wrong? How this analysis doesn't fit the evidence as well, and I'd say better, than your theory? I can explain the central maxima. You can't. I can explain the double slit pattern. I can explain where the envelope is, what's creating it. You can't. So come on, fess up. You took a wrong turn. Physics has made a few mistakes along with what it's done well. It's done some things very badly. And what you've done very badly is taken elemental functions, fundamental understandings, and perverted them. You've created a lot of fakes in your environment. The fake 1/2 mv squared, the fake two slit stuff, and the fake bent space crap. And have some integrity, make a counter argument to why this simple explanation isn't the correct explanation. Yeah, do that. Put up for a change. Well, I guess I could just end it with the typical ending. Should be able to anyway. So, this has been a Draft Science video presentation. Till the next time, and such.